Close your eyes for a moment. Not because I want you to stop paying attention, but because I want you to truly imagine something. Imagine you are standing inside a spacecraft. Not the kind you've seen launched from Cape Canaveral, not the cramped capsules that carried astronauts to the International Space Station, but something else entirely. Something that does not yet exist in our world, but might, just might exist in the future that awaits our grandchildren or their grandchildren. You are standing in a room that feels perfectly normal. The floor beneath your feet is solid. There is no vibration. There is no roar of engines. A cup of coffee sits on a table beside you, and the liquid inside it is perfectly still, not a single ripple on its surface. Everything feels calm, ordinary, almost boring, but then you walk over to the window, and what you see outside that window changes everything you thought you knew about reality. The stars are not points of light anymore. They are streaks, long, luminous lines of blue and white, stretched across the blackness of space like someone has taken a cosmic paintbrush and dragged it across the universe. They are moving, or rather, you are moving, though you cannot feel it at all. You look down at your watch. 3 hours have passed since you left Earth. Just 3 hours. But if you could somehow call home right now, if you could somehow reach back across the void to the little blue planet where you were born, you would discover something that would make your knees buckle. On Earth, 40 years have passed. 4 decades. The people you left behind have aged. Some of them are gone. The world has changed in ways you cannot even begin to fathom. And you, standing here with your still cup of coffee and your 3-hour journey, have barely aged at all. This is not a scene from a movie. This is not a fantasy conjured by a science fiction writer sitting in a dimly lit room. This is what the mathematics of our universe actually predicts. This is what Einstein's equations tell us is possible when you begin to approach and then surpass the speed of light. And here is the part that will keep you listening for the next hour and a half. In December of 2025, a team of scientists published a paper that sent shockwaves through the physics community. They announced that they had developed the first fully physically realized model for a warp drive. Not a warp drive that requires impossible exotic matter. Not a warp drive that exists only in the realm of pure mathematics. A warp drive built on physics that we already understand. A warp drive that, at least on paper, could one day carry human beings across the stars at 10 times the speed of light. 10 times. Let that number wash over you for a moment. 10 times the speed of light means that a journey to the nearest star, a journey that would take our fastest current spacecraft approximately 77,000 years, could be completed in a matter of months. It means that the galaxy, that vast, swirling collection of hundreds of billions of stars that we gaze up at on clear nights, would no longer be a prison. It would be a neighborhood. And so tonight in this documentary we are going to take you on a journey. Not just through the physics of faster-than-light travel, though we will cover that in extraordinary depth. Not just through the history of the scientists who dared to ask whether the impossible might actually be possible, though we will tell their stories too. We are going to take you on a journey through the very nature of reality itself. We are going to explore why the speed of light is the speed limit of the universe. We are going to understand what happens to time and space when you push against that limit. We are going to discover the brilliant, elegant loophole that Einstein's own equations left open, a loophole that a Mexican physicist watching Star Trek one evening in 1994 was the first to fully articulate. We are going to trace the path from that initial theoretical breakthrough through NASA's secretive Eagleworks laboratory, through the groundbreaking work of applied physics, and all the way to the papers published in late 2025 and early 2026 that have brought warp drive closer to reality than it has ever been. We will talk about tachyons, those ghostly hypothetical particles that can only exist if they travel faster than light. We will talk about quantum entanglement, that eerie phenomenon that Einstein himself called spooky action at a distance, where two particles separated by billions of miles seem to communicate instantaneously. We will talk about wormholes, those theoretical tunnels through the fabric of space-time that could connect distant corners of the universe. We will talk about time dilation and the twin paradox, about what happens to your body and your experience of time when you travel at 99% the speed of light. We will talk about the Kardashev scale and what kind of civilization humanity would need to become in order to harness the energy required for warp drive. And we will talk about what it would actually feel like to travel faster than light, what you would see, what you would experience, and what the universe would look like from inside a warp bubble traveling at 10 times the speed of light. But before we launch into all of that, before we dive into the deep waters of physics and mathematics and the nature of space-time, let me ask you a few questions. These are not trick questions. They are genuine questions designed to show you just how strange, how wonderful, and how deeply counterintuitive our universe truly is. Are you ready? Here's the first one. Do you know how fast light actually travels? Most people know it is fast. Some people know the number, but very few people truly grasp what that number means. Light travels at 299,792,458 meters per second. That is approximately 300,000 kilometers per second, or 186,282 miles per second. To put that in perspective, if you could travel at the speed of light, you could circle the entire Earth 7.5 times in a single second. You could travel from New York to Los Angeles in approximately 13 thousandths of a second. In the time it takes you to blink your eyes, light has traveled across a distance greater than the width of the United States. Now, here is the second question, and this one is where it starts to get unsettling. Do you know how far away the nearest star is? Not our sun, of course, but the nearest star beyond our solar system. That star is called Proxima Centauri, and it is part of the Alpha Centauri system, a triple star system that is the closest stellar neighbor to our sun. Proxima Centauri is 4.24 light-years away. A light-year is the distance that light travels in 1 year, which works out to approximately 9.46 trillion kilometers, or 5.88 trillion miles. So Proxima Centauri is about 40 trillion kilometers away, and even traveling at the speed of light, the fastest speed the universe allows, it would take you 4 years and 3 months to get there. 4 years. At the fastest speed possible. Now, here's the third question. Do you know how long it would take to get to Proxima Centauri with our current technology? Voyager 1, launched in 1977, is the fastest spacecraft humanity has ever sent into deep space. It is currently traveling at approximately 62,000 kilometers per hour, or about 38,000 miles per hour. That is fast by human standards, but at that speed, it would take Voyager 1 approximately 77,000 years to reach Proxima Centauri. 77,000 years. To put that in context, 77,000 years ago, anatomically modern humans were still sharing the planet with Neanderthals. The entirety of recorded human civilization, every empire, every war, every scientific discovery, every work of art, everything that we think of as human history spans only about 5 to 10,000 years. And it would take 15 times that long just to reach the nearest star with our best current technology. That is the scale of the problem we are dealing with. That is why faster-than-light travel is not just an interesting theoretical exercise. It is, in a very real sense, the most important technological challenge humanity has ever faced, because without it, we are trapped. We are confined to this one solar system, orbiting this one star, in this one corner of this one galaxy, and the universe is vast beyond imagination. Our Milky Way galaxy alone contains between 100 and 400 billion stars. The observable universe contains approximately 2 trillion galaxies. The nearest large galaxy, Andromeda, is 2.5 million light-years away. At the speed of Voyager 1, it would take approximately 46 billion years to reach Andromeda, which is more than 3 times the current age of the universe. So when scientists say they have found a way to travel 10 times faster than light, this is not just an academic curiosity. This is potentially the key that unlocks the universe for humanity. This is potentially the difference between a species confined to one pale blue dot and a species that walks among the stars. And this is exactly why you should be paying attention to what I am about to tell you over the next 90 minutes. Now, before we go any further, before we dive into the deep physics, I want to say something directly to you. If you are the kind of person who is fascinated by these questions, if the vastness of the cosmos fills you with wonder rather than despair, if you have ever lain awake at night staring at the ceiling and wondering what is really out there, then you are exactly the person this documentary was made for. You are part of a community of curious minds, people who refuse to accept that the impossible is truly impossible, people who believe that the universe rewards those who dare to ask the biggest questions. And if that describes you, I would love for you to join this community permanently. Hit that subscribe button right now, tap that bell icon so you never miss a deep dive like this one, and drop a comment below telling me, do you believe humans will ever travel faster than light? I genuinely want to know what you think, because I have been going back and forth on this question myself throughout the entire process of researching this documentary, and I am curious whether you will land where I landed by the end. Now, with that said, let us begin at the very beginning. Let us talk about light itself. Light is perhaps the most extraordinary thing in the universe. It is simultaneously the simplest and the most mysterious phenomenon we have ever encountered. At its most basic, light is electromagnetic radiation, a self-propagating wave of electric and magnetic fields that oscillates through space. But that clinical description does not begin to capture what light truly is or why it occupies such a singular position in the laws of physics. The story of how we came to understand light is one of the great intellectual adventures of human history, and it begins long before Einstein, long before the 20th century, in the mind of a Scottish physicist named James Clerk Maxwell. In the 1860s, Maxwell achieved something extraordinary. He unified the previously separate phenomena of electricity and magnetism into a single theoretical framework, encapsulated in what we now call Maxwell's equations. These 4 equations, which you can fit on a postcard, describe how electric charges create electric fields, how moving charges create magnetic fields, and how changing electric fields create magnetic fields and vice versa. But the truly astonishing thing Maxwell discovered was that his equations predicted the existence of electromagnetic waves, disturbances in the electric and magnetic fields that would propagate through space at a specific speed. And when Maxwell calculated that speed, he got a number that was eerily familiar. It was approximately 300,000 kilometers per second, the speed of light. This was a thunderbolt moment in the history of physics. Maxwell had not set out to explain light. He had set out to understand electricity and magnetism. But his equations were telling him that light itself was an electromagnetic wave, and they were telling him something else, something that would not be fully appreciated for another 40 years. They were telling him that this speed, the speed of light, was a fundamental constant of nature. It did not depend on the motion of the source. It did not depend on the motion of the observer. It was always the same. Always 300,000 kilometers per second. This was deeply strange. Think about how speed normally works in everyday life. If you are standing on the sidewalk and a car drives past you at 60 miles per hour, you measure its speed as 60 miles per hour. But if you are driving in another car in the same direction at 30 miles per hour, you measure the first car's speed as only 30 miles per hour. Speeds add and subtract depending on the motion of the observer. This is basic, intuitive, common-sense physics. It is called Galilean relativity, and it works perfectly for cars and trains and baseballs. But Maxwell's equations were saying that light does not work this way. If a beam of light passes you at 300,000 kilometers per second, and you start chasing that beam at half the speed of light, you do not measure the beam's speed as 150,000 kilometers per second. You measure it as 300,000 kilometers per second, the full speed. No matter how fast you go, the speed of light is always the same. This made no sense to the physicists of the late 19th century. It seemed to contradict everything they knew about how motion works. And so they tried to explain it away. They proposed the existence of a substance called the luminiferous ether, a hypothetical medium that permeated all of space and through which light waves supposedly traveled, much as sound waves travel through air. If the ether existed, then the speed of light would be constant relative to the ether, and the strange predictions of Maxwell's equations could be explained. But in 1887, two American physicists named Albert Michelson and Edward Morley performed one of the most important experiments in the history of science. They attempted to detect the motion of the Earth through the luminiferous ether by measuring whether the speed of light was different in different directions. The logic was simple. If the Earth is moving through the ether, then light traveling in the direction of Earth's motion should be slightly slower, and light traveling perpendicular to Earth's motion should be slightly faster. The difference would be tiny, but Michelson and Morley had built an extraordinarily sensitive instrument, an interferometer, capable of detecting such tiny differences. The result was shocking. There was no difference. The speed of light was exactly the same in every direction. The ether did not exist. This result, known as the Michelson-Morley experiment, plunged physics into a crisis. If there was no ether, then why was the speed of light constant? How could it be that no matter how you moved, no matter how fast you traveled, light always moved at the same speed relative to you? The answer came in 1905 from a 26-year-old patent clerk in Bern, Switzerland, named Albert Einstein. And his answer would reshape our understanding of the universe more profoundly than any other idea in the history of human thought. Einstein's special theory of relativity, published in 1905 in a paper titled On the Electrodynamics of Moving Bodies, is built on two simple postulates. Just two. The first postulate states that the laws of physics are the same for all observers who are moving at constant velocities relative to each other. This is called the principle of relativity, and it is actually not new. Galileo had articulated a version of it centuries earlier. It simply means that there is no experiment you can perform inside a smoothly moving train that will tell you whether the train is moving or standing still. Physics works the same way regardless of your state of uniform motion. The second postulate is the revolutionary one. It states that the speed of light in a vacuum is the same for all observers, regardless of the motion of the light source or the motion of the observer. This is the direct embrace of what Maxwell's equations predicted, and what the Michelson-Morley experiment confirmed. Einstein did not try to explain away the constancy of the speed of light. He accepted it as a fundamental fact about the universe and asked, what are the consequences? The consequences, it turned out, were staggering. If the speed of light is truly constant for all observers, then something else must give. And what gives, Einstein showed, is our intuitive understanding of space and time. space and time are not the rigid, absolute frameworks that Isaac Newton imagined. They are flexible, malleable, and deeply interconnected. They form a four-dimensional fabric that Einstein and his former mathematics professor, Hermann Minkowski, called space-time. And when you move through space, it affects how you move through time, and vice versa. This leads to several extraordinary predictions, each of which has been confirmed by experiment countless times over the past century. The first prediction is time dilation. A moving clock runs slower than a stationary clock. If you are on a spaceship traveling at high speed relative to Earth, time literally passes more slowly for you than it does for people on Earth. This is not a trick of perception. It is not that your clock is malfunctioning. Time itself is passing more slowly for you. The second prediction is length contraction. A moving object is physically shorter in the direction of its motion than an identical object at rest. If a spaceship passes you at 90% the speed of light, it will appear compressed, squished along its direction of travel. The third prediction is the relativity of simultaneity. Two events that appear simultaneous to one observer may not be simultaneous to another observer moving at a different velocity. There is no absolute present moment that all observers share. The fourth prediction, and arguably the most famous, is encapsulated in the equation E equals mc squared. Energy equals mass times the speed of light squared. This equation tells us that mass and energy are two forms of the same thing, and they are related by the speed of light squared. Because the speed of light is such a large number, and because it is squared in this equation, even a tiny amount of mass contains an enormous amount of energy. 1 kilogram of matter, if converted entirely into energy, would release approximately 90 million billion joules of energy, which is roughly equivalent to the energy released by a 21 megaton nuclear weapon. This equation is the foundation of nuclear energy and nuclear weapons. It is the reason the sun shines, converting about 4 million tons of mass into energy every second through nuclear fusion. And it is deeply relevant to our story about faster-than-light travel, as we will see. But perhaps the most important consequence of special relativity for our purposes is what it says about the speed of light as a cosmic speed limit. Einstein's equations show that as an object with mass accelerates, its relativistic mass increases. The closer it gets to the speed of light, the more massive it becomes, and the more energy is required to accelerate it further. As the object approaches the speed of light, its relativistic mass approaches infinity. And to accelerate an infinite mass, you would need an infinite amount of energy. Since infinite energy does not exist, no object with mass can ever reach the speed of light, let alone exceed it. This is not a technological limitation. It is not something that better engines or more fuel could overcome. It is a fundamental property of the universe, woven into the very fabric of space-time. The speed of light is not just a speed. It is the speed at which causality propagates. It is the speed at which information, influence, and cause and effect travel through the universe. Nothing, absolutely nothing, can carry information faster than light. Or so it seems. Let me give you an analogy to help this sink in. Imagine you're trying to push a shopping cart across a parking lot. At first, the cart is easy to push, but with every step you take, the cart gets heavier. By the time you have crossed half the parking lot, the cart weighs as much as a car. By the time you are 3/4 of the way across, it weighs as much as a building. And as you approach the far edge of the parking lot, the cart becomes infinitely heavy. No matter how hard you push, you cannot move it another inch. That is what accelerating toward the speed of light is like for any object with mass. Photons, the particles of light, can travel at the speed of light because they have zero rest mass. They do not experience this problem. but anything with mass, whether it is an electron, a proton, a spaceship, or a human being, faces this insurmountable barrier. Now, there is a deeper reason why the speed of light serves as this ultimate cosmic boundary, and it has to do with causality. Causality is the principle that causes precede their effects. You throw a ball, and then the window breaks. Not the other way around. You flip a switch, and then the light turns on. This seems obvious, almost trivially true. But here's the thing. Einstein showed that if anything could travel faster than light, it could arrive at its destination before the light from its departure event. This would mean that, from certain frames of reference, the effect would happen before the cause. The window would break before you threw the ball. The light would turn on before you flipped the switch. This is not just philosophically strange. It leads to genuine logical paradoxes. The most famous is the grandfather paradox. If you could travel faster than light, you could, in principle, travel backwards in time. And if you could travel backwards in time, you could, in principle, go back and prevent your own grandfather from meeting your grandmother. But then you would never have been born. And if you were never born, you could never have traveled back in time to prevent their meeting. Which means they would have met, which means you would have been born. And around it goes, in an infinite logical loop that makes no sense. This is why physicists take the speed of light barrier so seriously. It is not just about speed. It is about protecting the logical consistency of the universe. It is about ensuring that the chain of cause and effect, the very thing that makes reality coherent, is never broken. And yet, as we are about to discover, the universe has left open a loophole. A stunning, elegant, mind-bending loophole that scientists are only now beginning to fully understand. Let us pause here for a moment and let all of that settle. Take a deep breath. Feel the weight of what we have just discussed. The speed of light is not merely fast. It is the fundamental speed of the universe. The speed at which causality itself travels, the speed that defines the relationship between space and time. And nothing with mass can ever reach it, because to do so would require infinite energy, and surpassing it would break the logical fabric of reality. If this were the end of the story, then faster-than-light travel would be truly, absolutely, permanently impossible. We would be trapped in our solar system forever, prisoners of the light-speed barrier. But this is not the end of the story. It is, in fact, barely the beginning. Because in 1915, 10 years after publishing Special Relativity, Einstein published another theory. A theory that was even more revolutionary, even more beautiful, and even more strange. A theory that would reveal the loophole. That theory is called general relativity. Special relativity deals with objects moving at constant velocities. It describes the behavior of space and time for observers who are not accelerating. But the real universe is full of acceleration, most notably the acceleration caused by gravity. Einstein spent 10 years, from 1905 to 1915, working to extend his theory to include gravity and acceleration. The result was the general theory of relativity, and it is widely regarded as one of the greatest intellectual achievements in human history. The core insight of general relativity is breathtaking in its simplicity and profundity. Gravity is not a force. Let me say that again, because it contradicts everything you were probably taught in school. Gravity is not a force. In Newton's picture of the universe, gravity is a force that reaches out across space and pulls objects toward each other. The Earth pulls on the Moon, the Sun pulls on the Earth, and so on. But Einstein showed that this picture is wrong, or at least incomplete. Gravity is not a force pulling objects together. Gravity is the curvature of space-time caused by the presence of mass and energy. Massive objects like stars and planets warp the fabric of space-time around them, creating curves and dips. Other objects then follow these curves, not because they are being pulled, but because they are following the straightest possible path through curved space-time. This straightest possible path is called a geodesic, and it is the closest thing to a straight line that exists in curved space. The classic analogy is a bowling ball on a trampoline. Place a heavy bowling ball in the center of a trampoline, and it creates a dip, a curve in the fabric. Now roll a marble across the trampoline. The marble does not travel in a straight line. It curves toward the bowling ball, following the shape of the dipped fabric. It looks like the bowling ball is pulling the marble, but really, the marble is just following the curvature of the trampoline's surface. This is how gravity works, according to Einstein. The Earth does not pull you toward its surface. The Earth warps the space-time around it, creating a curve that your body follows. You feel this as gravity, as weight, as the sensation of being pulled downward. But you're not being pulled. You are following the curvature of space-time. The mathematical framework of general relativity is Einstein's field equations, a set of 10 interlinked differential equations that describe exactly how the presence of mass and energy curves space-time, and how that curvature affects the motion of objects. These equations are notoriously difficult to solve, and exact solutions exist for only a handful of special cases. But those solutions have produced some of the most remarkable predictions in the history of science, virtually all of which have been confirmed by observation and experiment. General relativity predicts the existence of black holes, regions where space-time is curved so extremely that not even light can escape. This was confirmed observationally in 2019 when the Event Horizon Telescope captured the first direct image of a black hole's shadow. General relativity predicts that time runs slower in stronger gravitational fields, an effect called gravitational time dilation. This has been confirmed countless times, from precise measurements using atomic clocks at different altitudes to the corrections required by the GPS satellite system, which must account for both the special relativistic time dilation due to the satellite's orbital speed and the gravitational time dilation due to their altitude. General relativity predicts that massive objects bend the path of light, an effect called gravitational lensing. This was first confirmed during a solar eclipse in 1919, when Arthur Eddington observed that the positions of stars near the Sun were slightly shifted from their expected positions, exactly as Einstein had predicted. General relativity predicts the existence of gravitational waves, ripples in the fabric of space-time produced by the acceleration of massive objects. This was confirmed in 2015 by the LIGO detector, which measured gravitational waves produced by the merger of two black holes over 1 billion light-years away. This confirmation, exactly 100 years after Einstein's publication of general relativity, was one of the greatest experimental achievements of the 21st century. But for our story, the most important prediction of general relativity is something that is often overlooked, something that hides in plain sight within Einstein's equations but whose implications are absolutely staggering. It is this: there is no speed limit for space-time itself. Let me explain what this means, because it is the key to everything that follows. Special relativity tells us that no object can travel through space-time faster than light. This is the cosmic speed limit we discussed earlier. But general relativity tells us something different about space-time itself. Space-time is not a fixed, rigid stage on which events play out. It is a dynamic, flexible fabric that can stretch, compress, bend, warp, and ripple. And there is no law of physics, none whatsoever, that limits how fast space-time itself can change shape. The most dramatic illustration of this is the expansion of the universe. In 1929, astronomer Edwin Hubble discovered that distant galaxies are moving away from us, and the farther away they are, the faster they are receding. This was the first observational evidence of the expansion of the universe. But here is the critical point. These galaxies are not moving through space. The space between them is expanding, and there is no limit to how fast space can expand. In the first tiny fraction of a second after the Big Bang, the universe underwent a period of incredibly rapid expansion called cosmic inflation. During inflation, the universe expanded by a factor of at least 10 to the power of 26 in roughly 10 to the power of negative 32 seconds. That is an expansion rate vastly, incomprehensibly faster than the speed of light. The space between points in the universe was stretching faster than light could cross it. And this did not violate Einstein's speed limit, because nothing was moving through space faster than light. Space itself was expanding. Similarly, today, galaxies at the edge of the observable universe are receding from us at speeds greater than the speed of light. This is not because they are hurtling through space at superluminal velocities. It is because the cumulative expansion of space across billions of light years results in a recession velocity that exceeds the speed of light. We can still see these galaxies because the light they emitted long ago, when they were closer, has had time to reach us. But the galaxies themselves are now beyond what is called the cosmic event horizon, and any light they emit today will never reach us, no matter how long we wait. So here's the loophole, stated as clearly and simply as I can state it. Einstein's speed limit says that nothing can travel through space-time faster than light. But space-time itself can move, stretch, compress, and warp at any speed it likes. If you could find a way to manipulate space-time itself, to compress the space in front of you and expand the space behind you, then you would not be traveling through space. You would be riding a wave of space-time. And that wave could carry you faster than light without you ever violating Einstein's cosmic speed limit. You would be like a surfer on a wave. The surfer does not swim through the water. The wave carries the surfer. And while there is a maximum speed at which a person can swim through water, there is no such limit on how fast a wave can travel. This is the idea at the heart of warp drive. This is the loophole that makes faster-than-light travel theoretically possible within the framework of Einstein's own general relativity. And the first person to rigorously work out the mathematics of this idea was a physicist named Miguel Alcubierre. Now, I want to take you back to the year 1994. The world was a different place. The internet was in its infancy. The Cold War had just ended. And in the city of Cardiff, Wales, a young Mexican theoretical physicist named Miguel Alcubierre was settling in for an evening of one of his favorite television shows, Star Trek: The Next Generation. Alcubierre was fascinated by the show's depiction of the warp drive, the fictional propulsion system that allowed the Starship Enterprise to travel faster than light. Unlike many scientists who dismissed warp drive as pure fantasy, Alcubierre was intrigued by the underlying concept. The warp drive in Star Trek works by creating a bubble of warped space-time around the ship. Inside the bubble, the ship is stationary, but the bubble itself moves through space at faster-than-light speeds, carrying the ship with it. Alcubierre wondered, could this actually work? Not in the simplified, hand-wavy way that Star Trek presented it, but rigorously, within the framework of general relativity. Could you write down a space-time metric, a mathematical description of the shape of space-time that would produce this kind of effect? He sat down and did the math, and to his astonishment, the answer was yes. In 1994, Alcubierre published a paper in the journal Classical and Quantum Gravity titled The Warp Drive, Hyper-Fast Travel Within General Relativity. In this paper, he presented a specific solution to Einstein's field equations that described a bubble of flat space-time moving through the universe at an arbitrary velocity, including velocities faster than light. The mathematics was rigorous, elegant, and entirely consistent with general relativity. Here is how it works. Imagine a region of flat, normal space-time. This is the passenger area, where the ship and its crew reside. Around this flat region, Alcubierre described a shell of curved space-time. In front of the bubble, space-time is contracted, compressed, squeezed together. Behind the bubble, space-time is expanded, stretched out. The combined effect of this contraction and expansion moves the bubble forward through the larger space-time, carrying the flat region and its contents along with it. The key insight, and this is absolutely critical, is that inside the bubble there is no motion at all. The ship is not moving through space. It is sitting still in its little pocket of flat space-time. But that pocket is being carried along by the wave of a space-time distortion, like a surfer carried by an ocean wave. And because it is space-time itself that is moving, not the ship, the light speed barrier does not apply. The ship never exceeds the speed of light within its local frame of reference. It is space-time that is doing the superluminal heavy lifting. Alcubierre used an analogy that I find particularly helpful. Imagine a tablecloth laid out on a long table, with a plate sitting on it near one end. Now imagine grabbing the tablecloth near the far end and pulling it toward you, bunching up the fabric in front of the plate and stretching it behind the plate. The plate moves along the table, not because any force is pushing it, but because the fabric underneath it is being rearranged. The plate, in this analogy, is the spaceship. The tablecloth is space-time, and the act of pulling the fabric is the warp drive. The plate does not slide across the tablecloth, it stays in the same spot on the cloth. But the cloth, and the plate along with it, moves across the table. Now, let me describe the mathematics a bit more precisely because the details matter. Alcubierre wrote down what is called a metric, which is a mathematical object that describes the geometry of space-time. His metric includes a function that he called the shift vector, which determines how fast the bubble moves. This shift vector can be set to any value, including values greater than the speed of light. Inside the bubble, the spacetime is described by the Minkowski metric, which is the flat, everyday spacetime of special relativity. Outside the bubble, spacetime is also approximately flat. But the shell of the bubble itself is a region of extreme curvature where spacetime is being compressed in front and expanded behind. The beauty of Alcubierre's solution is that it satisfies Einstein's field equations. It is a legitimate solution to the equations of general relativity. This means that the kind of spacetime geometry described by the Alcubierre metric is, at least in principle, allowed by the laws of physics as we currently understand them. But there are enormous problems with the Alcubierre drive, and to understand why warp drive is still not a reality, we need to discuss these problems in detail. The first and most significant problem is the requirement for exotic matter, specifically matter with negative energy density. Einstein's field equations relate the geometry of spacetime to the distribution of mass and energy. If you specify a particular spacetime geometry, the equations tell you what kind of matter and energy you would need to create that geometry. When Alcubierre plugged his warp drive metric into Einstein's field equations, the equations told him that the matter needed to create the warp bubble would have to have negative energy density. In other words, it would need to be a form of matter that has less energy than the vacuum of empty space. This is called exotic matter, and it is deeply problematic. In our everyday experience, and in virtually all of known physics, energy is always positive. A rock has positive energy. A photon has positive energy. Even the vacuum of empty space has, in most formulations, zero or positive energy. Negative energy is, as far as we know, not something that exists in nature on the scales required for a warp drive. There is a tiny exception, which we will discuss later, involving the Casimir effect, but it operates on scales so small as to be practically irrelevant for building a spacecraft-sized warp bubble. The requirement for exotic matter is not just an engineering problem, it is a fundamental physics problem. The laws of physics, as we currently understand them, include certain conditions called energy conditions that essentially state that energy should be positive. The most commonly cited is the weak energy condition, which says that any time-like observer should measure a positive energy density. The Alcubierre drive violates this condition. This does not necessarily mean the drive is impossible, because some physicists argue that the energy conditions are guidelines rather than absolute laws, and there are quantum effects that can violate them. But it is a very serious obstacle. The second problem is the sheer amount of energy required. When physicists first calculated the energy needed to create an Alcubierre warp bubble, the numbers were staggering. The original estimate suggested that you would need an amount of energy equivalent to the mass energy of the entire observable universe, roughly 10 to the power of 69 joules. This was, to put it mildly, not encouraging. Later refinements by various physicists, including NASA's Harold "Sonny" White, reduced this estimate significantly. White showed that by changing the shape of the warp bubble from a flat ring to a thicker, more toroidal shape, and by oscillating the bubble's intensity, the energy requirements could be brought down to something more manageable, perhaps equivalent to the mass energy of a Voyager 1-sized spacecraft. This was a reduction of many orders of magnitude, but even the most optimistic estimates still require an enormous amount of energy, far beyond anything humanity can currently produce. And remember, this energy would need to be in the form of exotic matter with negative energy density, which we do not know how to create at all. The third problem is what is sometimes called the horizon problem. Inside the warp bubble, the ship is surrounded by a shell of extremely curved space-time. The front edge of this shell, where space-time is being compressed, is analogous to an event horizon. Signals from inside the bubble cannot reach the front edge. This means that the pilot of the ship cannot send commands to the front of the bubble. They cannot steer. They cannot accelerate or decelerate the bubble from within. The bubble would need to be set up and controlled from outside, which raises the question of who is doing the controlling and how. Some physicists have suggested that the bubble would need to be pre-programmed before launch, with its entire trajectory calculated in advance. Others have proposed workarounds involving quantum effects or modifications to the bubble geometry. But this remains an unsolved problem. The fourth problem concerns radiation. In 2012, physicists showed that as the warp bubble travels through space, it would accumulate particles from the quantum vacuum at its front edge. These particles would be blue-shifted to extremely high energies, building up a concentrated wall of radiation at the front of the bubble. When the bubble decelerates, all of this accumulated energy would be released in a catastrophic burst of radiation that could sterilize anything in front of the ship. Arriving at your destination could mean destroying it. This is clearly not ideal for an interstellar travel system. The fifth problem involves causality violations. As we discussed earlier, anything that travels faster than light can, in principle, be used to send information into the past. This leads to logical paradoxes and violations of causality. Some physicists have argued that this means faster-than-light travel must be fundamentally impossible, regardless of what the mathematics of general relativity seems to allow. Others have proposed that there might be a self-consistency principle, like the Novikov self-consistency principle, that would prevent paradoxes from arising even if faster-than-light travel were possible. This debate is ongoing and unresolved. The sixth problem is that you cannot create the warp bubble from a standing start. To distort space-time in the way required by the Alcubierre metric, you would need to arrange the exotic matter in the correct configuration along the entire path of travel before the journey begins. In other words, someone would need to have already traveled to your destination, or at least set up the necessary space-time distortions in advance, using conventional means. This is a chicken-and-egg problem that significantly limits the practical utility of the Alcubierre drive. Despite all these problems, and they are serious problems, the Alcubierre drive was a watershed moment in the history of physics. Before 1994, faster-than-light travel was considered impossible by virtually all physicists. After 1994, it was considered merely incredibly difficult. That is an enormous shift. Alcubierre showed that the mathematics of general relativity does not forbid warp drive. The laws of physics, as we understand them, leave the door open, even if only a crack. And cracks have a tendency to be pried open by determined minds. As Alcubierre himself said, the fact that it is possible, even theoretically, is the important thing. And so, the race was on. Scientists around the world began working on refinements, modifications, and alternatives to the Alcubierre drive, each trying to solve one or more of its fundamental problems. And one of the most significant efforts came from an unlikely place, a laboratory tucked away inside NASA's Johnson Space Center in Houston, Texas. Let me tell you about Harold Sonny White and NASA's Eagleworks laboratory, because this is one of the most fascinating chapters in the story of warp drive research. White is a physicist who served as the Advanced Propulsion Theme Lead for the NASA Engineering Directorate. In that role, he led a small but dedicated team at the Johnson Space Center whose mission was to investigate advanced propulsion concepts, including ideas that most physicists would consider speculative at best and impossible at worst. The team's laboratory was nicknamed Eagleworks, and its existence signaled something remarkable, that the world's premier space agency considered warp drive research worthy of at least some investment of time and resources. White's primary contribution to warp drive physics was a modification of the Alcubierre metric that dramatically reduced the energy requirements. His key insight was that the original Alcubierre drive assumed a very specific shape for the warp bubble, one that was thin and flat like a disk. White showed that by making the bubble thicker, essentially changing its cross-section from a thin ring to a fat donut shape, the energy requirements dropped by many orders of magnitude. He also showed that oscillating the intensity of the warp field could reduce the energy requirements further. Where the original Alcubierre drive required energy equivalent to the mass of Jupiter, White's modifications brought the requirement down to something in the range of a few hundred kilograms to a few metric tons, depending on the specific parameters. This was still an enormous amount of energy, but it was within the realm of conceivability rather than being in the realm of the patently absurd. White went further than just theoretical work. He proposed and built an experiment to detect microscale space-time distortions in the laboratory. The experiment, called the White-Jude warp field interferometer, used a modified Michelson interferometer to look for tiny changes in the phase of a laser beam that might indicate that space-time was being warped. The idea was not to create a warp bubble, which would have required far more energy than the experiment could produce, but to detect whether it was possible to create even the tiniest perturbation in the geometry of space-time using electromagnetic fields. The results of the White-Jude experiment were, unfortunately, inconclusive. Some early reports suggested that the interferometer had detected a signal consistent with space-time distortion, but these results were never replicated and were met with significant skepticism from the broader physics community. Many physicists argued that the signals were artifacts of the experimental setup rather than genuine space-time distortions. White's credibility was further complicated by the M-drive controversy. The M-drive is a device proposed by British engineer Roger Scheuer that claimed to produce thrust without any propellant, appearing to violate Newton's third law of motion. White and his Eagleworks team tested the M-drive and initially reported positive results, leading to a wave of media excitement. However, subsequent experiments by other teams, including a rigorous study by physicists at the Dresden University of Technology, showed that the apparent thrust was an artifact of thermal effects and experimental error. The M-drive does not work. This episode cast a shadow over Eagleworks' credibility and, by extension, over the warp drive research being conducted there. Nevertheless, White's theoretical work on reducing the energy requirements of the Alcubierre drive was an important contribution that has been cited and built upon by subsequent researchers. And White's willingness to take warp drive seriously within the institutional framework of NASA helped to legitimize the field and attract the attention of other physicists who might otherwise have dismissed it as fringe science. The fact that NASA, an organization with a well-earned reputation for rigorous engineering and cautious science, was willing to devote resources to warp drive research sent a powerful signal that this was a topic worthy of serious investigation. While NASA's Eagleworks was conducting its experiments, a very different approach to warp drive research was taking shape at a company called Applied Physics. Founded by Gianni Martira and joined by astrophysicist Alexei Bobrik, Applied Physics is a public benefit company that works with governments and the private sector on problems in advanced physics. Bobrik had first encountered warp drive research while studying general relativity in college, and the idea had stuck with him. When he met Martyr and learned of his interest in the topic, the two decided to investigate warp drive from scratch, using a fundamentally different approach from what had been attempted before. The key decision they made was to not start from the Alcubierre metric and try to fix its problems. Instead, they decided to start from the most basic physical principles and ask a simpler question: what is the most general possible description of a warp bubble that is consistent with known physics? This bottom-up approach led to a breakthrough that would change the field. In 2021, Bobrik and Martyr published a paper in the journal Classical and Quantum Gravity titled Introducing Physical Warp Drives. The title was carefully chosen, and the word physical was key. Previous warp drive proposals, including Alcubierre's original drive, were mathematical solutions to Einstein's equations that required exotic matter with negative energy density that does not appear to exist in our universe. These proposals were mathematically valid, but physically unrealizable. Bobrik and Martyr's paper described, for the first time, a warp bubble that could be constructed using only normal, positive energy matter. No exotic matter, no negative energy, no violations of the energy conditions. The geometry they described consists of an inner region of flat space-time. This is the passenger area, where the laws of physics operate normally, surrounded by a curved outer shell that acts like a gravitational field. The outer shell is made of normal matter arranged in a specific configuration that creates the desired curvature of space-time. This is fundamentally different from the Alcubierre drive in an important way. Alcubierre's warp bubble does not gravitationally interact with objects outside the bubble. It is, in a sense, invisible to the rest of the universe. This is one of the features that makes it unphysical, because in general relativity, any concentration of mass energy should have a gravitational influence on its surroundings. Bobbrick and Martier's warp bubble does have a gravitational influence. It warps the spacetime around it in a detectable way. This makes it more physical, more consistent with how we know the universe actually works. However, and this is a significant caveat, the 2021 model has an important limitation. It can only move at speeds below the speed of light, subluminal speeds. This might seem like a disappointment. After all, the whole point of warp drive is to go faster than light, right? But physicists who understand the significance of this work see it differently. The 2021 paper was not about achieving faster-than-light travel immediately. It was about establishing that warp bubbles, actual physical configurations of matter and spacetime that move through the universe carrying a flat interior region, are possible within known physics. This had never been demonstrated before. Every previous warp drive proposal required exotic matter, and therefore existed outside the realm of known physics. Bobbrick and Martier showed that the basic concept of a warp bubble is physically valid. They laid the foundation. The speed, they believed, would come later. The response from the scientific community was significant. The paper was published in a top-tier peer-reviewed journal, which means it passed the scrutiny of expert reviewers. It was covered in major scientific media outlets, and perhaps most remarkably, Miguel Alcubierre himself reviewed the work and endorsed it. The originator of the warp drive concept looked at what Bobbrick and Martier had done and said, "This is an important step forward." Sabine Hassenfelder, a physicist and prominent science communicator, commented that, "Now we have a much better mathematical basis to study warp drives." She described the paper as a significant advance in our understanding of what warp bubbles are and how they might work. Applied Physics also developed a computational tool called the Warp Factory, which allows researchers to input different spacetime configurations and test whether they satisfy the energy conditions and other physical requirements. This tool was open-sourced to the scientific community, enabling distributed research and accelerating progress in the field. It was the first numerical implementation of physical warp drive analysis, and it has been used by research groups around the world. Then came December 2025, and the announcement that made headlines across the globe. Scientists at Applied Physics published a new paper that took the 2021 work several critical steps further. The headlines were dramatic. Scientists announce a physical warp drive is now possible. Seriously. This paper, also published in Classical and Quantum Gravity, presented what the authors described as a fully physically realized model for warp drive. Let me unpack what fully physically realized means because it is important. The 2021 model showed that subluminal warp bubbles were possible with positive energy. The 2025 model went further. It described a complete physical model that includes not just the geometry of the warp bubble, but also a detailed description of the matter configuration needed to create it, using only matter that obeys the known laws of physics. The paper introduced the concept of floating spacetime bubbles, as opposed to floating ships in spacetime. The distinction is subtle but profound. In the Alcubierre drive, you have a ship sitting in a bubble of flat spacetime, and the bubble moves through the larger spacetime. In the new model, the bubble itself is the fundamental object. It is a self-contained region of spacetime with specific properties, and the ship is simply the flat interior of the bubble. This reconceptualization allowed the authors to describe the warp bubble in a way that capitalized on the inherent properties of spacetime rather than fighting against them. They showed that spacetime bubbles can, in principle, behave in ways that are not limited by the speed of objects within them. The paper also presented a method for constructing such bubbles based on fully understood laws of physics. The mass requirements were still enormous, roughly equivalent to the mass of several Jupiters, but the theoretical path from concept to construction was laid out more clearly than it had ever been before. In the same month, December 2025, another paper was published that showed warp drive metrics could be designed to fit the shapes of actual starships, like those envisioned in Star Trek. This was not just a mathematical curiosity. It demonstrated that the abstract geometries of warp drive physics could be mapped onto practical spacecraft designs, moving the concept from pure mathematics into what might be called engineering-adjacent territory. And in early 2026, new studies continued to push the boundaries, proposing that spacetime might bend more readily than previously thought, and refining the mathematical tools used to analyze warp drive geometries. The pace of research is accelerating. More papers are being published on warp drive now than at any point in history. More physicists are taking the concept seriously, and the mathematical foundations are becoming more robust with each new publication. Now I want to take a step back and look at the bigger picture, because warp drive is not the only theoretical path to faster-than-light travel. There are other ideas, some more speculative and some less so, that approach the problem from entirely different angles. Understanding these alternatives gives us a richer picture of the landscape of superluminal travel, and helps us appreciate why the warp drive concept has emerged as the most promising candidate. Let us start with tachyons, one of the most intriguing concepts in theoretical physics. The word tachyon comes from the Greek word tachys, meaning swift or fast. Tachyons are hypothetical particles that always travel faster than light. They were first seriously proposed by physicist Gerald Feinberg in 1967, although the concept had been discussed informally before then. The idea behind tachyons is fascinating because it turns our normal understanding of particles on its head. Normal particles, which physicists call tardions or bradyons, always travel slower than light. As they gain energy, they speed up, approaching but never reaching the speed of light. Photons, which are called luxons, always travel at exactly the speed of light, with zero rest mass. Tachyons, if they exist, would occupy the third category, particles that always travel faster than light. In the tachyon framework, the speed of light is still a barrier, but it is a barrier from the other side. Just as normal particles cannot be accelerated to the speed of light because their relativistic mass would become infinite, tachyons cannot be decelerated to the speed of light for the same reason. As tachyons lose energy, they speed up. As they gain energy, they slow down, approaching the speed of light from above but never reaching it. The fastest tachyon would have zero energy, and its speed would be infinite. To make the mathematics work, tachyons must have what is called imaginary mass. Not imaginary in the everyday sense of being made up, but imaginary in the mathematical sense of being the square root of a negative number. When you plug an imaginary mass into the equations of special relativity, the resulting particle naturally travels faster than light. And the equations still work. They do not produce contradictions or infinities. They simply describe a different kind of particle than we are used to. In 2024, physicists published research suggesting that tachyons could be reconciled with special relativity using a revised theoretical framework that preserves the fundamental principle of causality. This was a significant development because one of the main arguments against tachyons was that their existence would inevitably lead to causal paradoxes. The new framework suggested that this might not be the case. The tachyons could exist without breaking the chain of cause and effect. However, and this is a very big however, no tachyon has ever been detected experimentally. There is no observational evidence that tachyons exist. The most famous near miss came in 2011, when the OPERA experiment at CERN appeared to detect neutrinos traveling faster than the speed of light. The announcement sent shockwaves through the physics community. If neutrinos could travel faster than light, it would have been the most important discovery in physics in a century. But the result turned out to be wrong. A loose fiber optic cable and a faulty clock in the timing system had introduced an error in the measurement. When the error was corrected, the neutrinos were traveling at exactly the speed you would expect. The speed of light, or very slightly below it. The opera episode was a sobering reminder that in physics, extraordinary claims require extraordinary evidence. As of now, tachyons remain a theoretical curiosity, a mathematical possibility that may or may not correspond to anything in the real universe. Now, let us talk about quantum entanglement, because this is one of the most commonly misunderstood phenomena in all of physics, and it is directly relevant to the question of faster-than-light communication. Quantum entanglement occurs when two particles become correlated in such a way that the quantum state of each particle cannot be described independently of the other, even when the particles are separated by vast distances. When you measure a property of one entangled particle, you instantly know the corresponding property of the other particle, regardless of how far apart they are. This correlation is instantaneous. It appears to happen with no delay at all, not even the delay you would expect from a signal traveling at the speed of light. Einstein was deeply troubled by this. He referred to it as spukhaft Fernwirkung, German for spooky action at a distance, and he argued that it meant quantum mechanics was incomplete, that there must be some hidden variables that determined the particle's states in advance, before the measurement was made. In 1964, physicist John Stuart Bell derived a set of inequalities, now called Bell's inequalities, that could distinguish between quantum mechanics and any theory based on hidden variables. Numerous experiments since then, most definitively the experiments by Alain Aspect in the 1980s and the loophole-free Bell tests of 2015, have consistently shown that Bell's inequalities are violated, confirming that quantum entanglement is real and not the result of hidden variables. Entanglement is genuine, non-local, and instantaneous. So does this mean we can communicate faster than light using entangled particles? The answer, unfortunately, is no. And the reason is both subtle and profound. When you measure one entangled particle, you do indeed instantly affect the state of the other particle. But the measurement result you get is random. You cannot control what result you get. And without being able to control the result, you cannot encode information in it. The measurement of one particle gives you a random outcome, and the measurement of the other particle gives you a correlated random outcome. But random outcomes, even correlated ones, do not carry information. To extract useful information from entanglement, you need to compare the results of measurements on both particles. And that comparison requires a classical communication channel, one that travels at or below the speed of light. This is formalized in what is called the no-communication theorem, which proves mathematically that entanglement cannot be used to transmit information faster than light. So entanglement is genuinely non-local, but it is not useful for faster-than-light communication. It is a connection, but not a telephone line. However, and I want to emphasize this, the non-locality of entanglement does hint at something deep about the structure of reality. It tells us that the universe is more interconnected than our classical intuitions suggest. It tells us that space, the thing that separates entangled particles, may not be as fundamental as we think. Some theoretical physicists, notably those working on quantum gravity, have proposed that entanglement might be the very thing that stitches space-time together. This idea, sometimes called ER equals EPR, a conjecture proposed by physicists Juan Maldacena and Leonard Susskind, suggests that entangled particles are connected by tiny wormholes, microscopic tunnels through space-time. If this conjecture is correct, then the relationship between entanglement and spacetime geometry may hold the key to understanding not just quantum mechanics, but gravity itself. And that, in turn, might one day lead to new insights about whether and how spacetime can be manipulated for faster-than-light travel. Let me now talk about quantum tunneling, another quantum phenomenon that has sometimes been invoked in discussions of faster-than-light effects. Quantum tunneling is the process by which a particle passes through a barrier that it does not have enough energy to climb over classically. In classical physics, if a ball does not have enough energy to roll over a hill, it will bounce back. In quantum physics, there is a probability that the ball will simply appear on the other side of the hill, having tunneled through it. This is not science fiction. It happens all the time. It is the mechanism by which alpha particles escape from atomic nuclei in radioactive decay. It is the mechanism by which electrons flow through the barriers in tunnel diodes and other semiconductor devices. It is even a crucial step in nuclear fusion inside stars. The reason tunneling is relevant to our discussion is that there have been experiments suggesting that the tunneling process can occur faster than light. In particular, a phenomenon called the Hartmann effect shows that for very thick barriers, the tunneling time does not increase with the thickness of the barrier. This seems to imply that the particle is crossing the barrier at superluminal speed. However, the consensus among physicists is that this does not represent true faster-than-light information transfer. The tunneled signal arrives faster than expected, but its leading edge does not travel faster than light. The information encoded in the signal cannot be extracted faster than light. The effect is more like receiving the beginning of a wave slightly earlier than expected, rather than actually transmitting a message superluminally. It is a subtle but important distinction. Now, let me tell you about some of the more exotic theoretical proposals for faster-than-light travel. These are concepts that go beyond warp drive and into even more speculative territory, but they are all based on legitimate physics and have been studied by serious physicists. The first is the Krasnikov tube, proposed by Russian physicist Sergei Krasnikov in 1995. A Krasnikov tube is essentially a tube of modified spacetime connecting two distant points. The idea is that a spacecraft would first travel from point A to point B at subluminal speed, and as it traveled, it would modify the spacetime behind it, creating a tube of spacetime in which the return journey could be made faster than light. Think of it as building a highway as you drive. The first trip takes a long time, but once the highway is built, subsequent trips are much faster. The advantage of a Krasnikov tube over a warp drive is that it does not require the spacecraft to travel faster than light on the initial journey. The tube is built at subluminal speed, and only the return trip, or subsequent trips by other travelers, benefits from the superluminal shortcut. However, Krasnikov tubes, like the Alcubierre drive, require exotic matter to construct, and they also raise concerns about causality violations, since they could potentially be used to create closed time-like curves. The second exotic proposal involves wormholes, also known as Einstein-Rosen bridges. Wormholes are theoretical shortcuts through spacetime that connect two distant points via a tunnel through a higher dimension of space. Imagine taking a piece of paper and drawing two dots on it, one near the top and one near the bottom. The shortest path between the dots along the surface of the paper is a straight line. But if you fold the paper so that the two dots are close together, and then poke a hole through the paper, you can create a path between the dots that is much shorter than the path along the surface. This is the basic idea of a wormhole. The spacetime around us is like the surface of the paper, and the wormhole is the shortcut through the fold. Wormholes are predicted by general relativity. In 1935, Einstein and his collaborator Nathan Rosen showed that the equations of general relativity allow for the existence of bridges connecting two separate regions of spacetime. These Einstein-Rosen bridges, as they were called, were originally understood as mathematical curiosities rather than physical objects. But subsequent work by physicists, including Kip Thorne, showed that if wormholes could be stabilized, they could in principle be used for faster-than-light travel, and even time travel. The problem, once again, is exotic matter. To keep a wormhole open, you would need to line its throat with matter that has negative energy density. Without this exotic matter, the wormhole would collapse before anything could pass through it. And, as we have discussed, negative energy matter does not appear to exist in our universe on the required scales. Nevertheless, wormholes remain a fascinating theoretical possibility, and they continue to be studied by physicists who are trying to understand the deep structure of spacetime. The third exotic proposal involves cosmic strings. Cosmic strings are hypothetical, one-dimensional defects in spacetime that might have been created during phase transitions in the early universe. Think of them as cracks in spacetime, incredibly thin, but potentially stretching across vast cosmic distances. If two cosmic strings pass each other at high speed, the spacetime between them could, according to some calculations, create a path that would allow an object to travel between 2 points faster than light. The physicist J. Richard Gott proposed this scenario in 1991, showing that two infinitely long cosmic strings passing each other could create closed time-like curves, which is physicists' way of saying time travel. However, subsequent work showed that the energy conditions required for cosmic string time travel are probably not satisfied in the real universe, and no cosmic strings have ever been observed, though they remain a prediction of some models of the early universe. Now, let me bring our discussion back to the practical realm and talk about the propulsion technologies that humanity actually has, or is developing, that could take us to the stars, even without faster-than-light travel. This is important context because it highlights just how desperately we need a breakthrough like warp drive if we want to explore even our immediate cosmic neighborhood. The current state-of-the-art in space propulsion is chemical rockets. The Saturn V rocket that took astronauts to the moon used kerosene and liquid oxygen, and its exhaust velocity, the speed at which propellant exits the engine, was about 4.5 kilometers per second. Modern rockets use slightly more efficient propellants, but the basic performance is similar. The fastest spacecraft humanity has ever launched is the Parker Solar Probe, which reached a speed of approximately 635,000 kilometers per hour, or about 0.06% of the speed of light, as it fell toward the Sun. At that speed, it would take the Parker Solar Probe about 6,600 years to reach Proxima Centauri. Voyager 1, our most distant spacecraft, is traveling at about 61,000 kilometers per hour and would take about 77,000 years. Ion drives represent a step up from chemical propulsion. They work by using electric fields to accelerate ions to very high speeds, producing a small but sustained thrust that can gradually build up to high velocities over time. NASA's Dawn spacecraft used an ion drive to visit the asteroid Vesta and the dwarf planet Ceres. Ion drives are much more efficient than chemical rockets in terms of fuel usage, but their thrust is very low, typically measured in millinewtons. A spacecraft with a sufficiently large and powerful ion drive, running for years or decades, could potentially reach speeds of a few percent of the speed of light. But even at 5% of the speed of light, the journey to Proxima Centauri would take about 85 years. Solar sails represent yet another approach. Instead of carrying fuel, a solar sail uses the pressure of sunlight to propel itself through space. Photons from the sun strike the sail's reflective surface and transfer momentum to it, slowly but steadily accelerating the spacecraft. The advantage of solar sails is that they carry no fuel, and can accelerate continuously for as long as there is sunlight. The disadvantage is that the acceleration is very small, and it decreases with distance from the sun as sunlight becomes dimmer. The Breakthrough Starshot project, funded by billionaire Yuri Milner, aims to send a fleet of tiny, gram-scale probes to Alpha Centauri, using ground-based lasers to push light sails to about 20% of the speed of light. At that speed, the probes would reach Alpha Centauri in about 20 years. However, these probes would be tiny, carrying only the most basic instruments, and they would fly past the Alpha Centauri system at 20% of the speed of light, giving them only a brief window for observations. They would not be able to slow down and enter orbit. Nuclear thermal propulsion uses a nuclear reactor to heat a propellant, typically hydrogen, to very high temperatures, producing a more powerful exhaust than chemical rockets. NASA has been developing nuclear thermal propulsion for potential Mars missions, and it could cut the transit time to Mars roughly in half compared to chemical rockets. But nuclear thermal propulsion is still far too slow for interstellar travel. Nuclear pulse propulsion, also known as Project Orion, is a more radical concept that was studied in the 1950s and 1960s. The idea is to detonate a series of small nuclear bombs behind the spacecraft, using the blast waves for propulsion. Project Orion calculations suggested that such a spacecraft could reach speeds of about 3 to 5% of the speed of light, which would allow it to reach Proxima Centauri in about 85 to 140 years. The concept is technically feasible, but it has obvious problems. The nuclear fallout from thousands of detonations, the weight of the bombs, and the political and environmental implications of nuclear testing in space. Fusion propulsion represents perhaps the most promising near-term technology for interstellar travel. Nuclear fusion, the same process that powers the sun, could in principle be harnessed to produce an incredibly powerful and efficient rocket engine. A fusion rocket could potentially reach speeds of 10% or more of the speed of light, which would allow it to reach Proxima Centauri in about 40 to 50 years. Several concepts have been proposed, including the Daedalus project designed by the British Interplanetary Society in the 1970s, which envisioned a fusion-powered probe that could reach Barnard's star in about 50 years. However, we have not yet achieved sustained, controlled nuclear fusion on Earth, let alone built a fusion rocket engine. The International Thermonuclear Experimental Reactor, or ITER, in southern France, is working toward demonstrating net energy gain from fusion. But even if it succeeds, adapting fusion technology for space propulsion would take additional decades of development. And then there is antimatter propulsion, the most energy-dense propulsion concept we know of. When matter meets antimatter, they annihilate each other completely, converting 100% of their combined mass into energy. This is far more efficient than nuclear fusion, which converts less than 1% of mass into energy, and incomparably more efficient than chemical rockets, which convert only a tiny fraction of a percent. A matter-antimatter propulsion system could theoretically reach speeds of up to 72% of the speed of light, according to recent studies. At such speeds, a spacecraft could reach Proxima Centauri in about 6 years. The problem is that antimatter is extraordinarily difficult and expensive to produce. Current particle accelerators can produce only nanograms of antimatter per year, and the cost is estimated at trillions of dollars per gram. Storing antimatter is equally challenging, since it annihilates on contact with any normal matter. Containing it requires electromagnetic traps that keep the antimatter suspended in a vacuum, away from the walls of any container. We are very, very far from producing the kilograms of antimatter that an interstellar mission would require. So here is the picture. Our best current technology, chemical rockets, would take tens of thousands of years to reach the nearest star. Advanced concepts like fusion drives and antimatter propulsion could reduce that to decades, but they remain far from realization. Only faster-than-light travel, or something close to it, could truly open the galaxy to human exploration within a single human lifetime. And that brings us back to warp drive. Now, I want to take you on a deeper exploration of what would actually happen if you were inside a spacecraft, traveling at 10 times the speed of light using a warp drive. What would you see? What would you feel? How would the universe appear from inside a warp bubble? This is one of the most fascinating and least discussed aspects of warp drive physics, and I think you will find it extraordinary. The first thing to understand is that inside the warp bubble everything is normal. Completely, boringly normal. The interior of the warp bubble is a region of flat space-time, described by the standard Minkowski metric. The laws of physics operate exactly as they do on Earth. Gravity is normal. Electromagnetic forces are normal. Your coffee sits still in its cup. You feel no acceleration, no deceleration, no sense of motion at all. This is fundamentally different from conventional space travel, where you would feel the acceleration of the engines pushing you forward. In a warp bubble, there is no acceleration. The ship is not moving through space. Space is moving around the ship. To an observer inside the bubble, it would feel like sitting in a stationary room. The only evidence that anything extraordinary is happening would come from looking out the windows. And what you see out the windows would be truly otherworldly. The extreme warping of space-time at the bubble wall would distort light from external sources in dramatic ways. Stars in front of you would be blue-shifted, their light compressed to shorter wavelengths. Stars behind you would be red-shifted, their light stretched to longer wavelengths. At 10 times the speed of light, these effects would be extreme. Stars ahead might shift from visible light into the ultraviolet, or even X-ray range, becoming invisible to the naked eye but potentially dangerous in terms of radiation. Stars behind might shift from visible light into the infrared, also becoming invisible. The view from the side windows would be the most interesting. Stars at right angles to your direction of travel would be relatively undistorted, and you would see them moving rapidly across the sky as you pass them. The overall visual effect would be a kind of cosmic kaleidoscope, with stars appearing to stream around the bubble like water flowing around a rock in a river. Now, let us talk about travel times, because this is where the warp drive concept truly reveals its transformative potential. At 10 times the speed of light, here is how long various journeys would take. The trip from Earth to the Moon, which currently takes about 3 days with conventional rockets, would take about 0.13 seconds. A tenth of a second. Before you could blink, you would be there. The trip from Earth to Mars, which currently takes 7 to 9 months, would take about 76 seconds, a little over a minute. You could leave Earth after breakfast and be on Mars before your coffee cools. The trip from Earth to Jupiter, which currently takes about 5 to 7 years for a robotic mission, would take about 4.5 minutes. The trip from Earth to Pluto would take about 33 minutes, half an hour to cross the entire solar system. The trip to Proxima Centauri, the nearest star, would take about 5 months. Not 77,000 years. 5 months. In less than half a year, you could be orbiting another star, looking at alien worlds, exploring a completely different solar system. The trip to Sirius, one of the brightest stars in the night sky, about 8.6 light-years away, would take about 10 months, less than a year to reach one of the most famous stars in human history. A trip to the TRAPPIST-1 system, about 40 light-years away and home to 7 Earth-sized planets, including several in the habitable zone, would take about 4 years. That is roughly the same as a tour of duty on a submarine. The trip to the center of the Milky Way, about 26,000 light-years away, would take about 2,600 years. Still a very long time, but conceivable for a generation ship or a civilization with advanced life extension technology. And a trip to the Andromeda Galaxy, our nearest large galactic neighbor at 2.5 million light-years, would take about 250,000 years. Even at 10 times the speed of light, intergalactic travel remains prohibitively long. You would need to travel at thousands or millions of times the speed of light to cross the voids between galaxies in a reasonable time frame. But within our own galaxy, 10 times the speed of light would be absolutely transformative. It would put thousands of star systems within reach within a human lifetime. It would enable the establishment of colonies around other stars. It would allow for ongoing communication between Earth and interstellar outposts, albeit with significant delays. It would open up the galaxy for exploration in a way that no other propulsion technology could match, and it would answer once and for all one of the most profound questions humanity has ever asked. Are we alone? Let me dwell on that last point for a moment, because the question of extraterrestrial life is intimately connected to the question of faster-than-light travel, and the connection runs deeper than you might think. It runs all the way to one of the most famous paradoxes in science, the Fermi Paradox. The Fermi Paradox is named after the Italian-American physicist Enrico Fermi, who in 1950 famously asked, "Where is everybody?" The logic behind his question is simple and devastating. The Milky Way galaxy is roughly 13 billion years old and contains hundreds of billions of stars. Many of those stars have planets. Some of those planets are inhabitable zones, where conditions might be right for life. Given the vast number of potential habitats and the vast amount of time available, it seems almost inevitable that intelligent life should have arisen many times throughout the galaxy's history. Some of those civilizations would presumably have developed technology far beyond our own. Some might have developed warp drive or other means of interstellar travel. And even at modest speeds well below the speed of light, a civilization with the motivation to expand could colonize the entire galaxy in a few million years, which is a tiny fraction of the galaxy's age. So, if intelligent life is common and interstellar travel is possible, the galaxy should be teeming with civilizations. We should see evidence of them everywhere. Radio signals, megastructures, colonized star systems, visiting probes, but we see nothing. The universe is silent. This is the Fermi Paradox. The silence is deafening. There are many proposed solutions to the Fermi Paradox, and they are relevant to our discussion because they are directly related to whether faster-than-light travel is possible. If FTL travel is possible and aliens exist, then the Fermi Paradox becomes even harder to explain. If you can cross the galaxy in thousands of years rather than millions, then even a single FTL-capable civilization should have spread everywhere by now. The fact that we see no evidence of this could mean several things. It could mean that FTL travel is impossible, that the barriers we have discussed, the need for exotic matter, the enormous energy requirements, the causality problems, are truly insurmountable, and no civilization, no matter how advanced, can overcome them. This would be a somber conclusion, because it would mean that the galaxy's star systems are effectively isolated islands, forever separated by the vast oceans of space between them. It could mean that FTL travel is possible but extremely rare, perhaps requiring a level of technological advancement that very few civilizations ever reach. This is related to the concept of the Great Filter, the idea that there is some step in the evolution of intelligent, spacefaring civilizations that is extraordinarily difficult to pass, and most civilizations are filtered out before they reach it. The development of FTL technology could be one such filter. It could mean that FTL-capable civilizations exist, but choose not to make their presence known. This is the basis of the dark forest theory, popularized by Chinese science fiction author Liu Cixin in his novel, The Dark Forest. According to this theory, the universe is like a dark forest in which every civilization is a silent hunter. Civilizations that reveal their presence are destroyed by other civilizations, so the smart survival strategy is to remain hidden. If this theory is correct, then the silence of the universe is not evidence of absence, but evidence of caution. It could also mean that FTL-capable aliens are already here, or have already visited, but in ways that we cannot detect or recognize. This idea veers into more speculative territory, but it is not inherently unscientific. A civilization millions of years ahead of us might have technology so advanced that they are indistinguishable from the natural universe. Their probes might be molecular-scale devices. Their presence might be woven into the fabric of space-time itself. The connection between FTL travel and the Fermi Paradox illustrates why this topic is so important. The question, can we travel faster than light, is not just a question about physics. It is a question about the nature and fate of intelligent life in the universe. Its answer will determine whether we are destined to remain alone on our little planet or whether we can join a cosmic community of civilizations spanning the stars. Now, let me return to the physics and address a topic that is absolutely essential for understanding the deeper implications of faster-than-light travel. Time dilation. We touched on this earlier, but now I want to explore it in much greater depth, because it is one of the most profound and counterintuitive consequences of Einstein's theories, and it has direct bearing on the question of FTL travel and its implications for causality. Time dilation comes in two flavors: special relativistic time dilation, which is caused by relative motion, and gravitational time dilation, which is caused by gravity. Let us start with special relativistic time dilation. As we discussed, Einstein's special relativity shows that time passes more slowly for a moving object than for a stationary one. The amount of time dilation depends on the speed of the moving object, and is given by the Lorentz factor, gamma, which equals 1 divided by the square root of 1 minus v squared over c squared, where v is the speed of the object and c is the speed of light. Let me walk you through what this means at various speeds. At 10% of the speed of light, about 30,000 kilometers per second, the Lorentz factor is approximately 1.005. This means time passes about 0.5% more slowly for the moving observer. If you traveled at 10% of the speed of light for a year, you would arrive home to find that about 1.005 years had passed on Earth, a difference of about 2 days. Noticeable if you had very precise clocks, but not a dramatic effect. At 50% of the speed of light, about 150,000 kilometers per second, the Lorentz factor is approximately 1.15. Time passes about 15% more slowly. A 1-year trip at this speed would mean about 1.15 years pass on Earth, a difference of about 2 months. At 90% of the speed of light, the Lorentz factor jumps to approximately 2.29. Time passes about 56% more slowly. A 1-year trip means about 2.29 years on Earth, a difference of about 15 months. At 99% of the speed of light, the Lorentz factor is approximately 7.09. Time passes about 7 times more slowly. A 1-year trip means about 7 years on Earth. At 99.9% of the speed of light, the Lorentz factor is approximately 22.4. A 1-year trip means about 22 years on Earth. At 99.99% of the speed of light, the Lorentz factor is approximately 70.7. A 1-year trip means about 71 years on Earth. a full human lifetime. And at 99.9999% of the speed of light, the Lorentz factor is approximately 707. A 1-year trip means about 707 years on Earth. The slower you travel through space, the faster you travel through time. And the faster you travel through space, the slower you travel through time. This is not a metaphor. It is a literal, physical reality. Now, here is where it gets truly mind-bending. What happens with time dilation inside a warp bubble? This is one of the most discussed and debated questions in warp drive physics, and the answer depends on the specific details of the warp drive design. In the Alcubierre drive, the interior of the warp bubble is flat spacetime. This means that for the passengers, time passes normally. There is no time dilation inside the bubble. The passengers do not age more slowly or more quickly than they would on Earth. But here is the crucial subtlety. The bubble is moving through the external spacetime faster than light. And in the external spacetime, the relationship between the bubble's departure and arrival events depends on the frame of reference of the external observer. For some external observers, the ship would appear to arrive at its destination before it left. This is the causality problem we discussed earlier, and it is one of the deepest unresolved issues in warp drive physics. For the applied physics model, which currently operates only at subliminal speeds, the time dilation situation is more straightforward. The passengers would experience some time dilation, similar to what you would experience traveling at the same speed without a warp drive. But the key advantage of the warp drive is that the passengers do not feel any acceleration. In conventional space travel at high speeds, the acceleration required to reach and maintain those speeds would be bone-crushing, requiring either extremely long acceleration periods or technologies we do not yet possess. The warp drive sidesteps this problem entirely because the ship is not accelerating through space. It is sitting still in its little pocket of flat spacetime, which is being carried along by the movement of spacetime itself. The twin paradox, which we mentioned earlier, takes on a new and fascinating dimension in the context of warp drive. In the conventional twin paradox, one twin stays on Earth while the other travels to a distant star at near light speed and returns. The traveling twin ages less than the Earth-bound twin due to time dilation. But in the warp drive version of the thought experiment, the traveling twin does not experience time dilation because the interior of the warp bubble is flat spacetime. The traveling twin ages at the same rate as the Earth-bound twin. If the warp drive is faster than light, the traveling twin could arrive at a distant star and return before the Earth-bound twin has aged more than a few months. There is no paradox in this scenario, at least not the time dilation kind. But there is a deeper paradox involving causality, as we have discussed. The warp drive twin paradox is not about who ages faster. It is about whether the traveling twin arrives before they left. Let me now talk about gravitational time dilation, because it is relevant to understanding how warp drive might affect time. Gravitational time dilation was predicted by Einstein's general relativity, and has been confirmed by numerous experiments. Time passes more slowly in stronger gravitational fields. A clock on the surface of the Earth runs slightly slower than a clock in orbit, because the surface of the Earth is deeper in the Earth's gravitational well. The effect is small, about 45 microseconds per day, but it is real and must be accounted for in precision timekeeping. A clock near a black hole would experience extreme gravitational time dilation. At the event horizon of a black hole, time, from the perspective of a distant observer, appears to stop entirely. This does not mean that the clock's owner experiences time stopping. From their perspective, time passes normally, but light and signals from the clock take longer and longer to reach the distant observer, eventually being stretched to infinite wavelengths and never arriving at all. This was vividly illustrated in the movie Interstellar. where the main character visits a planet orbiting very close to a massive black hole. Due to gravitational time dilation, 1 hour on the planet's surface corresponds to 7 years in orbit. The character's crew members waiting in orbit age decades, while he spends only a few hours on the surface. This is not science fiction invention. It is a direct consequence of Einstein's equations, and it represents a physically possible scenario, albeit one that is unlikely to be encountered in practice due to the extreme conditions near a black hole. The relevance to warp drive is that a warp bubble involves extreme curvature of space-time. The wall of the warp bubble is a region of very strong gravitational effects. Depending on the specific geometry of the bubble, there could be significant gravitational time dilation effects at the bubble wall, even if the interior of the bubble is flat. Understanding these effects is part of the ongoing research into warp drive physics. Let me now shift our focus to what is perhaps the most important practical question about warp drive: energy. How much energy would you need, and where would it come from? This is the question that separates theoretical possibility from practical reality, and the numbers are, to put it gently, daunting. As we discussed, the original Alcubierre drive required an amount of energy equivalent to the mass energy of the observable universe, approximately 10 to the power of 69 joules. Harold White at NASA reduced this to roughly the mass energy of Jupiter, about 2 times 10 to the power of 44 joules. The applied physics model requires roughly the mass energy of several Jupiters, which is similar. To put this in perspective, let me compare it to humanity's current energy production. The total energy produced by human civilization in a year is approximately 580 exajoules, or about 5.8 times 10 to the power of 20 joules. The mass energy of Jupiter is about 1.9 times 10 to the power of 44 joules. That means we would need to produce about 10 to the power of 24 times more energy than our entire civilization produces in a year. That is roughly 1 trillion times our current annual energy output. This number is so large that it is easy to dismiss warp drive as hopelessly impractical. But I want to put it in a different perspective. The Sun produces approximately 3.8 times 10 to the power of 26 watts, or about 1.2 times 10 to the power of 34 joules per year. A civilization that could harness the entire output of the Sun for about 1 million years could accumulate enough energy for a warp drive. Alternatively, a civilization that could harness the output of thousands of stars simultaneously could do it much faster. This brings us to the Kardashev scale, a framework for classifying civilizations based on their energy consumption. The scale was proposed by Soviet astronomer Nikolai Kardashev in 1964 and has 3 main levels. A Type 1 civilization, also called a planetary civilization, can harness all the energy available on its home planet. This includes all solar energy falling on the planet, all geothermal energy, all wind, tidal, and other energy sources. The total available energy for a Type 1 civilization is roughly 10 to the power of 16 to 10 to the power of 17 watts. Humanity is currently a Type 0.7 civilization on this scale, meaning we are not yet able to harness even the full energy resources of our own planet. A Type 2 civilization, also called a stellar civilization, can harness the entire energy output of its home star. The concept most commonly associated with a Type 2 civilization is the Dyson sphere, a hypothetical megastructure that completely surrounds a star and captures all of its energy output. A Type 2 civilization would have access to approximately 10 to the power of 26 watts, about 1 billion times more energy than a Type 1 civilization. A Type 3 civilization, also called a galactic civilization, can harness the energy of an entire galaxy. This would involve capturing the output of hundreds of billions of stars, giving the civilization access to approximately 10 to the power of 36 watts. To build and operate a warp drive, humanity would likely need to be at least a Type 2 civilization, capable of harnessing the full output of the sun. Physicist Michio Kaku has estimated that humanity could reach Type 1 status within 1 to 200 years, and Type 2 status within perhaps a few thousand years, depending on the rate of technological progress. These are speculative estimates, of course, but they suggest that warp drive might be achievable on timescales of thousands of years rather than millions, which is a blink of an eye in cosmic terms. There is another possibility, however, one that is more speculative, but potentially more near-term. What if the energy requirements for warp drive can be further reduced? Every time physicists have revisited the warp drive problem, they have found ways to reduce the energy requirements. Alcubierre's original estimate required the mass energy of the universe. Harold White reduced it to the mass energy of Jupiter. The applied physics team has been working on further reductions. It is conceivable that continued theoretical work could reduce the energy requirements to the point where a warp drive becomes feasible for a civilization at or near Type 1 status. Some physicists have speculated that a deeper understanding of quantum gravity, the as-yet undiscovered theory that unifies general relativity and quantum mechanics, might reveal entirely new ways to manipulate space-time that require far less energy than our current theories predict. This is speculative, but it is not unreasonable. Major revolutions in physics have often led to dramatic practical consequences that were completely unforeseen. The discovery of quantum mechanics led to transistors, lasers, and the entire electronics industry. The discovery of nuclear physics led to nuclear energy. A future discovery about the nature of space-time could lead to technologies we cannot currently imagine. Let me now talk about the Casimir effect, because it is one of the few known phenomena that produces something resembling the negative energy that many warp drive designs require. The Casimir effect, predicted by Dutch physicist Hendrik Casimir in 1948, occurs between two uncharged parallel metallic plates placed very close together in a vacuum. The vacuum of space is not truly empty. According to quantum mechanics, it is filled with virtual particles, particle-antiparticle pairs that constantly pop into existence and annihilate each other. These virtual particles exist at all wavelengths, creating what is called the quantum vacuum energy. When two metallic plates are placed very close together, only virtual particles with wavelengths that fit between the plates can exist in the gap. Virtual particles with longer wavelengths are excluded. This means there are fewer virtual particles between the plates than outside them. The result is a net pressure pushing the plates together, as if the vacuum between the plates has negative energy relative to the vacuum outside. The Casimir effect has been measured experimentally and is well established. It represents a real physical phenomenon where the energy between the plates is less than the surrounding vacuum energy. In a sense, the region between the plates has negative energy density relative to the vacuum. Some physicists have suggested that the Casimir effect could be a starting point for generating the negative energy needed for warp drive or wormhole stabilization. However, there are several major obstacles. First, the effect is extremely small. The Casimir pressure between two plates separated by 1 micrometer is about 0.01 newtons per square meter, roughly 100 million times weaker than atmospheric pressure. Second, the effect requires the plates to be extremely close together, on the order of nanometers to micrometers. Third, it is not clear that the Casimir effect produces true negative energy in the sense required by general relativity. The effect is a relative phenomenon, where the energy between the plates is lower than the energy outside, but the absolute energy may still be non-negative. Nevertheless, the Casimir effect demonstrates that the quantum vacuum is not as simple as classical physics suggests, and it opens the door to the possibility that more exotic quantum effects might someday produce the kind of negative energy that warp drive requires. I want to take a moment here to talk about something that is often overlooked in discussions of faster-than-light travel: the emotional and psychological impact. Imagine what it would mean for the human species to have access to warp drive. Imagine the moment when the first warp bubble is created in a laboratory. It might be a tiny bubble, lasting for a fraction of a second, far too small and brief to carry a spacecraft. But its creation would prove that space-time can be manipulated in the way warp drive requires. It would be the Wright brothers' moment for interstellar travel. The announcement would be front-page news on every publication on Earth. It would be the most significant scientific achievement since the discovery of fire. And it would change everything. It would change how we think about ourselves. For all of recorded history, humanity has been defined by the boundaries of Earth. Our wars, our cultures, our philosophies, our art, everything has been shaped by the fact that we are a single species on a single planet orbiting a single star. Warp drive would shatter that boundary. It would open the possibility of human beings living on worlds orbiting other stars, in star systems that are currently just points of light in the night sky. It would expand the definition of home from one world to millions. It would change how we think about time. As we have discussed, time dilation effects at near light speeds mean that interstellar travelers would be separated from their homeworlds not just by distance, but by time. A trip to a star 100 light-years away at near light speed would mean that everyone the traveler knew on Earth would be dead by the time they arrived, let alone by the time they returned. Warp drive could eliminate this problem, making round trips to distant stars possible within a single human lifetime, with no significant time difference between travelers and those who stay behind. It would change how we think about the Fermi Paradox. If warp drive is possible and we achieve it, we would know that other civilizations could have achieved it too. The question, "Where is everybody?" would become even more urgent and more puzzling. And it might eventually be answered not by telescopes or radio antennas, but by a warp-equipped ship arriving at a distant star system and finding unmistakable signs of another civilization. Now, let me discuss the fascinating connection between warp drive and gravitational waves, because this is one of the most exciting developments in recent warp drive research. In 2024, a group of physicists published a paper describing what would happen if a warp bubble collapsed, an event they called a warp core breach, borrowing the term from Star Trek. They showed that the collapse of a warp bubble would produce gravitational waves, ripples in space-time similar to those produced by colliding black holes or merging neutron stars. The gravitational wave signature of a warp core breach would be distinctive, different from any naturally occurring gravitational wave source. If we could tune our gravitational wave detectors to the right frequency, we might be able to detect such events from across the galaxy. This has a stunning implication. We might not need to build a warp drive ourselves to detect faster-than-light travel. If any civilization anywhere in the galaxy has achieved warp drive and ever experienced a malfunction, the gravitational waves from that event might be detectable from Earth. We could be searching for alien warp drives right now, using instruments we already have. The current generation of gravitational wave detectors, LIGO and Virgo, are sensitive to a specific range of frequencies, primarily those produced by merging black holes and neutron stars. A warp core breach might produce gravitational waves at different frequencies, requiring a different type of detector. But future gravitational wave observatories, like the Laser Interferometer Space Antenna, LISA, planned for launch in the 2030s, will be sensitive to a much broader range of frequencies. It is conceivable that one of these future detectors could pick up the signature of a distant warp core breach. As Aaron MacDonald, Star Trek's science advisor, put it, the notion that we might get a glimpse of other warp-capable species as a result of interstellar disasters is objectively awesome. Let me now address some of the philosophical implications of faster-than-light travel, because the physics is only part of the story. The deeper questions raised by FTL travel are philosophical, ethical, and existential in nature, and they deserve serious consideration. The first and most obvious philosophical implication is the question of time travel. As we have discussed, any form of faster-than-light travel, if it is truly superluminal, implies the possibility of sending information into the past. This is a direct consequence of special relativity and cannot be avoided. If you can travel from point A to point B faster than a beam of light, then there exist reference frames in which you arrived at point B before you left point A. This means that, in principle, faster-than-light travel could be used to construct a time machine. The implications of time travel are profound and deeply troubling. The grandfather paradox, which we discussed earlier, is just the tip of the iceberg. If time travel is possible, then the very concept of causality, the idea that causes precede their effects, is called into question. Every event in the universe could, in principle, be influenced by events in the future as well as events in the past. The deterministic chain of cause and effect that we take for granted could be replaced by a web of mutual influence that loops through time in ways that defy our intuition. Some physicists have proposed resolutions to this problem. Stephen Hawking proposed the chronology protection conjecture, which states that the laws of physics conspire to prevent time travel at the macroscopic level. According to Hawking, any attempt to create a time machine would be thwarted by quantum effects, such as the buildup of vacuum energy to levels that would destroy the time machine before it could be used. The Novikov self-consistency principle, proposed by Igor Novikov, takes a different approach. It states that if time travel is possible, then events must be self-consistent. You can travel back in time, but you cannot change the past. Any action you take in the past is already part of the timeline. If you go back to prevent your grandfather from meeting your grandmother, something will always prevent you from succeeding, because you obviously exist, which means your grandparents obviously met. The self-consistency principle does not say time travel is impossible. It says that time travel, if possible, would be constrained to loops that are logically consistent. There is also the many worlds interpretation of quantum mechanics, which offers yet another resolution. In the many worlds interpretation, every quantum event causes the universe to split into multiple branches, each corresponding to a different outcome. If time travel is possible, then traveling back in time might create a new branch of the universe rather than modifying the existing one. You could go back and prevent your grandparents from meeting, but this would create a new timeline in which you were never born. The original timeline, the one in which you were born and traveled back in time, would continue to exist unchanged. There would be no paradox, because the two events, your existence and your grandparents not meeting, happen in different branches of reality. This resolution is philosophically satisfying but empirically untestable, at least with our current understanding of physics. The second major philosophical implication of FTL travel is the expansion of the human moral and political sphere. Currently, all of humanity's political, economic, and social structures exist on a single planet. Our nations, our alliances, our conflicts are all bounded by the surface of Earth. Interstellar travel would break those boundaries. If humans establish colonies around other stars, those colonies would eventually develop their own cultures, their own political systems, their own identities. Over time, they might become as different from Earth as the Americas became from Europe, or even more so. Communication between star systems, even with warp drive, would involve significant delays. At 10 times the speed of light, a message from a colony 100 light-years away would take 10 years to arrive. This delay would make real-time governance impossible. Interstellar colonies would need to be self-governing, making decisions without waiting for instructions from Earth. This would inevitably lead to political fragmentation, the emergence of independent starfaring civilizations with their own agendas and interests. History suggests that such fragmentation often leads to conflict. The European colonization of the Americas led to centuries of war and exploitation. The fragmentation of the Roman Empire led to centuries of chaos and violence. And interstellar humanity might face similar challenges, but on a vastly larger scale. The potential for interstellar war, while speculative, is a sobering possibility that we should consider long before we develop the technology that would make it possible. The third philosophical implication is perhaps the most profound of all. Faster-than-light travel would fundamentally change our understanding of our place in the cosmos. For most of human history, Earth was the center of the universe, the stage on which the drama of existence played out. Then, Copernicus showed that Earth orbits the Sun. Then, Hubble showed that our galaxy is just one of billions. Each successive discovery has made humanity seem smaller, less significant, less special. But FTL travel would reverse this trend. It would make us larger, more expansive, more capable. It would transform us from a species confined to one planet into a species that spans the stars. It would make the universe not a vast, indifferent void, but a frontier, a challenge, an invitation. And it would force us to confront the deepest question of all. What is the purpose of intelligent life in a universe that seems to have made such life incredibly rare? Now, let me bring us to one of the most critical chapters of our story, the question of what we still do not know. Because for all the progress that has been made in warp drive research, there are enormous gaps in our understanding that must be filled before faster-than-light travel can become a reality. And some of those gaps are so fundamental that filling them might require entirely new physics. The first and most obvious gap is our lack of a theory of quantum gravity. General relativity describes gravity as the curvature of space-time caused by mass and energy. Quantum mechanics describes the behavior of matter and energy at the smallest scales. Both theories are extraordinarily successful in their respective domains. General relativity has been confirmed by every experimental test to which it has been subjected. Quantum mechanics is the most precisely tested theory in the history of science. But the two theories are fundamentally incompatible. They describe the universe in mutually contradictory ways, and any attempt to combine them produces mathematical infinities and nonsensical results. This incompatibility is not just an aesthetic problem. It means that our understanding of physics is incomplete. There are situations where both gravity and quantum effects are important, such as at the center of a black hole, or during the first moments of the Big Bang, where neither theory alone gives a correct description. We need a new theory, a theory of quantum gravity, that unifies general relativity and quantum mechanics into a single coherent framework. Several candidate theories of quantum gravity have been proposed, including string theory, loop quantum gravity, and causal set theory. But none of these has been experimentally confirmed, and all have significant unresolved problems. A complete theory of quantum gravity might reveal new things about the nature of space-time that are directly relevant to warp drive. It might show that space-time can be manipulated more easily than our current theories suggest. Or it might show that the loopholes we have been exploiting, the ability of space-time to move faster than light, are closed by quantum effects. It might show that negative energy is possible on macroscopic scales, or it might prove definitively that it is not. The point is that we do not know, and we will not know until we have a complete theory of quantum gravity. The second major gap in our understanding concerns dark energy. As we discussed, dark energy is the mysterious force that is driving the accelerating expansion of the universe. It constitutes approximately 68% of the total energy content of the universe, yet we have almost no understanding of what it is. We know it exists because we can measure its effects on the expansion rate of the universe, but we do not know what it is made of, why it has the value it does, or how it is distributed through space. Some physicists have suggested that dark energy might be the key to warp drive. If dark energy is a property of space-time itself, as some theories suggest, then understanding it might reveal how to manipulate space-time more effectively. If dark energy is a field that permeates all of space, then harnessing it might provide the energy source needed for warp drive. These ideas are highly speculative, but they are not without merit. Dark energy is the most abundant form of energy in the universe. If we could tap into even a tiny fraction of it, the energy requirements of warp drive might become manageable. The third gap concerns dark matter, which constitutes approximately 27% of the universe's mass energy content. Dark matter interacts gravitationally with normal matter, bending space-time around it, but it does not interact with light or any other form of electromagnetic radiation. We know it exists because of its gravitational effects on galaxies and galaxy clusters, but we do not know what it is made of. Some physicists have proposed that dark matter might consist of particles that interact through forces we have not yet discovered. Understanding these forces might open new avenues for manipulating space-time. The fourth gap is the most fundamental of all. We do not know whether there are laws of physics that we have not yet discovered. Everything we know about physics comes from observing the approximately 5% of the universe that consists of ordinary matter and energy. The remaining 95%, dark matter and dark energy, is largely unknown. It is entirely possible that there are forces, particles, or principles that are completely unknown to us, as unknown as electromagnetism was to the ancient Greeks. History has shown that major revolutions in physics tend to arrive unexpectedly. Before 1900, physicists thought they understood the universe almost completely. Then came quantum mechanics and relativity, which overturned everything. Before the 1990s, astronomers thought the expansion of the universe was slowing down. Then came the discovery of dark energy, which showed that the expansion is accelerating. The next revolution in physics could come tomorrow, or it could come in 100 years. But when it comes, it will likely open doors that we cannot currently even see. I want to take a moment now to discuss the connection between warp drive research and the broader landscape of theoretical physics, because this context is important for understanding why the field has been gaining momentum in recent years. Warp drive research does not exist in a vacuum. It is part of a broader effort to understand the nature of space-time, an effort that includes some of the most active and exciting areas of modern physics. One of the most important developments in theoretical physics in recent decades has been the realization that space-time might not be fundamental. That is, space-time might not be a basic ingredient of reality, but rather something that emerges from a deeper underlying structure. This idea has roots in both string theory and quantum information theory. In string theory, space-time emerges from the interactions of one-dimensional strings vibrating in a higher dimensional space. In quantum information theory, particularly in the work of physicists like Mark van Ramsdonk, space-time appears to emerge from the entanglement of quantum bits of information. If space-time is emergent rather than fundamental, then manipulating it might be more like rearranging information than bending a rigid structure. This could have profound implications for warp drive, suggesting that the manipulation of space-time might be achievable through quantum information processing rather than brute force energy expenditure. The ER equals EPR conjecture, which I mentioned earlier, is another example of this kind of thinking. Proposed by Juan Maldacena and Leonard Susskind, it suggests that entangled particles are connected by microscopic wormholes. If this is correct, then wormholes and entanglement are two sides of the same coin, and understanding one might unlock the other. A deeper understanding of entanglement could lead to a deeper understanding of wormholes, and vice versa. And a deeper understanding of wormholes could lead to practical methods for manipulating space-time. These are all speculative ideas, far from being confirmed experimentally. But they represent the cutting edge of theoretical physics, and they suggest that our current understanding of space-time is just the beginning. The deeper truths about the nature of space and time are yet to be discovered, and those truths might hold the key to technologies that we currently consider impossible.